For mathematical calculations with forces, it is advisable to use the Cartesian coordinate system. The Cartesian coordinate system consists of an axis in the horizontal, here the y-axis, an axis in the vertical, here the z-axis, and an axis in depth, here represented by the x-axis. Now, let us imagine a three-dimensional imaginary box. Here we draw a force from the origin of the coordinate system to the diagonal end of the imaginary box. We can now divide this force with the help of the Cartesian coordinate system into three components, which can be represented on the three axes of the coordinate system. One force component in the x-axis, one in the y-axis, and the last in the z-axis. If we have a scalar coefficient providing the magnitude of a force but not the direction, we make use of so-called unit vectors. These unit vectors always have the starting point in the origin of the coordinate system and have the length 1. How can we now determine the magnitude of a force if we only know the individual components? For this purpose, we first consider a right-angled triangle. The angle between the sides A and B is 90 degrees. The side C is calculated by the formula c squared equals a squared plus b squared. This formula is also called the Pythagoras Theorem. If we now take the root of both sides, c is the root of a squared plus b squared. Now, we try to apply the Pythagoras Theorem to our previous example. First, we have our Cartesian coordinate system again, then the imaginary three-dimensional box, and the force from the origin of the coordinate system to the diagonal end of the box. We break down the force into the three individual components, Fx, Fy, and Fz. We can now move the single component Fy to the bottom of the imaginary box. If we now add an auxiliary line d, we have created a right-angled triangle with a right angle of 90 degrees between Fx and the moved Fy. So we can now write down the Pythagoras theorem as d squared equals Fx squared plus Fy squared. If we now move Fz diagonally under the endpoint of f, we have again a right-angled triangle with the sides d, the moved Fz, and the force F. Here, the Pythagoras theorem is now f squared equals d squared plus Fz squared. If we now replace the d squared with the equation determined before, we can write f squared equals fx squared plus fy squared plus fz squared. Besides the Pythagoras theorem, we also use trigonometry in the mathematical calculation of forces. Shown here is a right-angled triangle with the sides A, B, and C. The opposite angles of the sides have the designations alpha, beta, and gamma. The angle gamma is with 90 degrees a right angle. The sides of the triangle have different names in trigonometry. We can take one of the two non-right angles to designate the sides. If we take the angle beta as the base, then the side A, that is the side adjacent to the angle beta, is the adjacent. The side B in this case is the opposite, and the side C, that is the side opposite the right angle, is always called the hypotenuse. The rules of trigonometry are as follows. The sine of beta is equal to the opposite divided by the hypotenuse, that is b divided by c. The cosine of beta is equal to the adjacent divided by the hypotenuse, that is a divided by c. Last tangent of beta is equal to the opposite divided by the adjacent, so B divided by A. If we would consider the angle alpha instead of the angle beta, the side A would be the opposite, B the adjacent, and C remains the hypotenuse.